Hi, I'm Elaine. Welcome to my podcast channel.
Hi, Mr. Williams. Could you please introduce yourself about your
Yeah.
field? What do you teach?
Yeah, I can do that. My name is Ben Williams. I'm an associate professor of mathematics here at UBC. I'm one of the topologists in the department. I've been here at UBC since 2013, so coming up to 10 years now. Before that, I spent some time in California. I'm originally from Ireland, which some people don't know about me. They say my accent doesn't sound very Irish, but to me it sounds Irish.
Yeah, it sounds Irish. Irish, yeah.
Thank you.
Totally. Is there any difference between this UK English accent versus Irish?
Yeah, there are notable differences between British and Irish accents, in particular the way people pronounce. Well, one thing that stands out to me is the T sound in a word like water and at the end of the word flight and so on. There's a tendency in Irish dialects to pronounce that more like an SH. So water and flight.
Mhm.
Subtle, but I still pronounce water in a way. I go into a restaurant and I ask people for water and they don't really know what I mean because I have to modify and ask for water.
Oh, that is really funny.
Yeah.
Yeah. So what are some of the courses that you've taught at UBC?
Lately, I've been mostly teaching two courses every year, and then a third course that changes. And the two courses I regularly teach are something I think that's very important, and I hope many of your listeners
Mhm.
will at some point take, which is I teach the matrix algebra course here. This is a very big course. It's usually got when I teach it in the fall, it usually has over 600 students spread over 5 or 6 sections, and those students are taken from all over the university, usually in the second year. It's after they've taken some calculus courses and passed those. They show up in the second year and we teach them matrices, which I think is a very, very important topic.
Yeah.
And then the other course that I've been teaching every year now since before the pandemic is a 400 level or fourth year honors math course called, I think, Introduction to Topology, or potentially just topology. The problem is I never remember what the courses are called. And this, in contrast to the other course, the matrices course, where the class sizes are like 180 students and there are 5 sections. For the upper class course, it's targeted only at people who are majoring in math, and even then, many students don't take it. So I usually have about 10 students.
Wow.
So it's a different vibe, to say
Right,
the least.
it's definitely a very different vibe. So I've also looked at some of your ratings, and they're really highly praised. So what are some of your unique teaching methods?
Well, first of all, I think that a lot of the teaching here at UBC is a high standard. I mean, people can always find something to complain about, but I don't think I have any unique teaching methods. One thing about me is I come from a family of teachers on both sides, really, particularly on my father's side. My father was he's retired now, but he was a professor as well. And my aunts and uncles are many of them teachers on that side. And a few of my aunts and uncles are teachers on my mother's side as well. So I think I grew up with this. And one thing I like about teaching is the aspect of performance. You know, you have to put on a little bit of a show. The course seems like a lot of fun in the first week, sometime after Labor Day, and the sun is sort of shining, and you're well rested, and everyone's having a good time, and it's 11 in the morning. And then by the time mid-November comes around, and it's raining, and it's been raining for 3 or 4 weeks without stop, because this is Vancouver, and everyone's tired, and everyone's got like 15 midterms.
That's
The
crazy.
students and also the instructors. Well, no, they don't have 15. I'm exaggerating, but they have many midterms.
Yep.
So people can, I don't blame them, fall asleep in lecture or not want to show up. So it's good to keep it at least a little bit interesting, and to make people enjoy the experience of learning mathematics as much as possible. So that's
Yep.
something I always strive for.
Mhm.
But I wouldn't say that this is unique.
Yeah, I
To me.
think that's pretty unique. That's a really good example. You previously mentioned that you switched from an English major to a math major. Could
No,
you
that's not quite correct. I'm sorry. I did a double major.
double major? Okay.
Yeah.
English and math?
That's right.
Cool.
And those were just things that I enjoyed doing. And perhaps I just suffered from a lack of imagination, because those are two topics that I did in high school.
Mhm.
The university system, of course, has many other things to offer. Many courses that I didn't take in high school might have been open to me. But for instance, I never went down a path of becoming a dinosaur hunter, a paleontologist, and I didn't, or an archaeologist, or I didn't get into earth sciences, because what I knew coming out of high school was I enjoyed reading and writing and doing mathematics. So I just continued doing that. Nobody told me to stop.
Mm, yeah. So who inspired you into topology? Or I actually look at your CV, and you mentioned that you do a lot of algebraic geometry. So is there someone who inspired you into doing that?
It's an interesting story. I must say the following happened to me when I went to grad school. I had come from a peculiar background, because I had come from Dublin. I did my undergraduate, and then I went to California for graduate studies. And the university I was in Dublin at the time had, as an undergraduate, had many mathematicians who were particularly active in algebra. So matrix theory, just multiplying matrices and other algebraic structures. And I had actually done an MSc degree there, with a mathematician by the name of Kevin Hutchinson, who I think was a very, very big inspiration to me.
Yeah.
And he had suggested this topic, which was a little bit topological, but also, I think, fundamentally algebraic. And then when I went to grad school, I knew relatively a lot of algebra, but in contrast to some of the students coming from North American schools, I had a weak background in analysis. So that is to say, the calculus. I have never, to my shame, I have never taken, I never took a real proper calculus of several variables course. Somehow I skipped that. And I have taken very little in the way of differential equations courses, or differential geometry. So I found it a sort of a struggle to do my first topology course, because it involved certain things that I hadn't seen before.
Mm-hmm.
And but what I did have was the background in algebra. Now, the grad school I was in at the time, the graduate program, was good for topology. So I kind of made my peace with the fact that I wasn't a very good topologist then, and built on my strength in algebra. So I always came to topology from a particular background, which was, I think, a little bit unusual.
Yeah. Do you think there's a connection between algebraic geometry and topology in some way?
Oh yeah, I mean, this is my business to an extent.
Yeah.
This is what I like. Um, so what we're doing, I think, is, well, first of all, let me say how I think of topology as a discipline, and it's actually many different fields, perhaps with a common history and a common starting point, but it branches out in many different ways. I think this is true of many things that people say, oh, this is a branch of mathematics, but actually, when you look at it, it's many different things, maybe with a common history or common topics, but certainly differences as well. Topology, I think, is Well, it's what happens when you're doing geometry, but instead of worrying about the specifics of geometry, the lengths and angles and curvatures, volumes and questions like this, you ask yourself about the qualitative properties of geometric objects. Does it have a hole? Does it have two holes? Does it contain a volume? So let me just think of say a hula hoop or a bicycle wheel, ignoring the spokes. Just let's say a bicycle tire or the or a ring. These all are topological spaces, or they're all geometric spaces with a hole in them.
Yep.
But if I were to take, say, a soccer ball or a balloon, this is another kind of space or geometric object that it contains in it a cavity, a hole in the middle of it. Now, those holes that I'm talking about, the hole in the ring and the hole in the balloon, well, one of them is really like a hole that you could put your finger in, and the other one is a cavity where you could, say, place some grains of rice. And so even though we would use the same English word perhaps to describe these holes, they are somehow dimensionally different. One is like a one-dimensional phenomenon, the hole in the ring, whereas the sphere has a two-dimensional, or maybe even three-dimensional. It's not quite clear how you should think of the hole. So now, why is this useful? Well, it's just one particular way of thinking about spaces. It's not, or geometric structures. Of course, it's not the. If you come at the life, your purpose in life is to solve problems in geometry, then well, the first thing you might do is just do geometry, do measurements, do constructions, measure curvatures, and so on, and think about the various absolute specifics of the problem. But it has turned out to be useful to think about what we might call topological features. And there's enough of complexity and richness just in there that a discipline has built up, initially designed perhaps to serve the needs of geometry, that I will call algebraic topology. And algebraic geometry is one of the ways of doing geometry, and algebraic topology was invented to serve the needs of geometry. So there is a connection there.
Definitely.
But the algebraic or the topology has also taken on something of a life of its own in the 100+ years of its history.
Yep.
So it now has applications or implications beyond what you might think of as the purely geometric.
Yeah. I really like how you make connections and analogies. It really makes mathematical knowledge really clear, and yeah, you probably do that in class as well. So that's your teaching feature.
Oh, thank you. But I would say this happens to me, or it used to. I don't take so many classes anymore. I'd often go to a class where I had a teacher who made everything seem very clear, and I think this is great, and I understand this. And then that can be beguiling. You can sort of be seduced into thinking you understand everything because it was presented well and you understood it in the moment.
Yep.
And then you go back and you try to solve a problem, and you realize actually I didn't understand everything at all. So watch out for that. Sometimes I think I wish some of my teachers had been worse. So I might have been less seduced.
Yeah, it's definitely a lot of my listeners or friends, they're really interested in this concept of Klein bottles. Could you explain how Klein bottles, or these weird shapes, work?
Oh, okay. So let's talk about some weird shapes. Right. So the question we're really thinking about here, I think, originally is that of orientability. So we're fairly familiar with orientations, I think, as things appear to us in three-dimensional space. For example, let's go back to the balloon. You can look at the balloon, and the balloon is this sort of vaguely spherical object. I presume. I mean, it could be a novelty balloon, but let's take an ordinary balloon. It's got, it's inflated. Somebody's tied a knot in it. It's this bouncing balloon, and it has what you might consider, yeah, it has what you would call an outside, right? And it has also an inside, and those are actually completely clearly defined to us in our minds. And here's how you distinguish them. This is going to sound stupid, but let's go with it. The outside is where all the stuff is, and the inside is much smaller.
Yeah.
Right? The inside somehow is bounded and finite. There's not infinite space there, but on the outside of the balloon is the whole world full of everything. So there's an outside and there's an inside. And that's orientation as it pertains to this kind of the surface of the balloon. Now, other surfaces that we might encounter, more surfaces like the surface of a page, there are two sides there. Now, we no longer have an outside or an inside, but it's fine. If I have a sheet of paper, I have one side and I have the other side. I have the front and the back, let's say. And I can distinguish them. Well, it doesn't come to me in life with a distinguished front and a distinguished back, but I could write F on the front and then B on the back, and then I would have a front side and a back side. So that's what we would call an orientable object. You can choose which side is the front and which is the back.
Mm-hmm.
Life may have chosen for you. For instance, it could be a photograph. I have a photograph, and there's a beautiful picture of my family on the front, and on the back there's just, I don't know. I guess people don't really have print photographs so much anymore, but maybe on the back there is like the brand of the company that made the paper or something.
Okay. Yeah.
Now let's think about the Mobius band. So how you make this is you take a long piece of ribbon or something, or paper, a long piece of paper, and ribbon is probably better, but it's harder to find. And you put in one twist in the ribbon, and then you attach it back up so as to make something rather like a cylinder. Now, if you were to just not do that twisting and you were to attach this thing back up again, you would get sort of a floppy ribbon cylinder, a loop of ribbon. And you could orient this. You could write F. If you didn't care too much about this ribbon, you could write F on one side of the ribbon and follow that all the way around. And you go around in a loop, and you come back to your F. And you would write B on the other side, follow that all the way around in a loop, and you get back to your B. Now let's break the ribbon open again, so it's just a strip, and twist it once. And now we'll glue it back up again, or whatever we were doing, stitching, I suppose. And start at the F and go all the way around, and at some point you will sort of, because of this twisting, you'll turn over, and by the time you get back to where you had written the F, you'll be on what looks like locally the other side of the ribbon. You'll be back on the B.
Cool.
And this is an example of this is a Mobius band, and this is a non-orientable surface. That's fine. It just is what it is. And this one is not especially wacky. They're fun to make. And you can experiment with them. What happens if you introduce not just a single twist, but a double twist, twisting twice?
Yes. And
it turns out to become orientable again. Or you twist 3 times, it's no longer orientable, and so on. One thing that's a little bit weird about these, this is a bugbear of mine, is people often use these to represent infinity.
Interesting.
But what distinguishes them from a much more pedestrian space, a cylinder, is that there's this twist in them. So there's a front and there's no front and no back. They're no longer orientable. But they're no more infinite than the older symbol of infinity, which is, say, the cylinder, because that has no boundary. Right, you just go around the cylinder. You can go on forever. They shouldn't particularly be used to stand for something infinite or boundless. Instead, they should be used to stand for something that's slightly twisted. Now, there are some higher dimensional analogs of these Mobius bands. Actually, I say higher dimensional. Let me get back to that point. There are other things that one can write down mathematically, express. Say this is a mathematically defined geometric object that are not orientable, but with very few exceptions. I mean, really, the only example that we actually can, with only the exceptions of the Mobius bands, these non-orientable objects have a hard time living in three-dimensional space, and there are good reasons for this, which would take too long to get into. But so let me try to explain slightly more complicated non-orientable objects. Well, before that, perhaps I should say something about what dimension means.
Sure.
This throws people.
Yeah.
Because we're used to thinking about 3 dimensions
Right.
where we live, and people are like, "Oh, the 4th dimension is time." Now, that's maybe, let me not do any physics here. But for me, to say an object is n-dimensional, or say something is n-dimensional, means that it requires n somehow independent numbers to describe it.
Right.
So let me describe, currently, let's say, I'm a human being, and I am located on the surface of the Earth. And I'm located at some point on the surface of the Earth, and we need 2 numbers to describe where I am. We would need, say, a latitude and a longitude.
Mm-hmm.
I don't know what the latitude and longitude of Vancouver are, but I'm there.
Okay.
Yeah. And we could also try to describe how high I am off the surface of the Earth at this point. Let's pretend, big pretense, let's pretend the Earth is a perfect sphere, and now here I am, I'm sitting, I don't know, about 3 meters off the surface of the Earth, because I am upstairs.
Yes.
Maybe a little bit more, actually, looking at this room. We've got high ceilings, so I may be 4 meters off the surface of the Earth. Anyway, so we could measure this, and we could figure out where exactly I am in 3D space relative to the center of the Earth. Fair enough. But then there's more stuff about me, one of which is that I'm facing some direction.
Mm-hmm.
Now, how many more variables would we need to describe the direction I am facing? Well, if we just care about which direction I'm facing, left or right, I need 1 variable to measure the angle I am making relative to, say, north. I actually don't know what direction I'm facing currently. I'm facing sort of east-northeast.
Yep.
So many degrees away from north. And then I could be facing up or down, right? And that's another number. So to describe my location and the direction that I am facing, we would need 5 parameters. We would need 2 for where I am on the surface of the Earth, and 1 to describe my altitude, not very high, and then 2 more to describe the direction I'm facing. And then we could describe a few other things about me. We could describe what the temperature is in this room. That would be another parameter. So as we describe more and more features of this entity that is me, we need more and more numbers. So the space of all possible configurations for me, let's imagine that has some dimensionality, which is the sum total of all the independent numbers we need to describe where I am, and how I'm feeling, and all that, and what direction I'm pointing, and all this sort of stuff. So it's quite reasonable to think about spaces that are high dimensional. Now, they typically don't correspond to geometric things that we think of in the usual sense. They're not like cones or pyramids, but they often can be used to describe systems or complicated objects, what states they're in, what directions they're pointing. One thing I didn't mention when I was talking about me and my location and my orientation and so on is we never measured my velocity or my acceleration, both of which I think currently, hopefully, are 0, but they might not be. I could be zooming out the door. I could be facing one direction and traveling in another, and that would give me, say, 2 more parameters if we're measuring both velocity and acceleration just on this surface. And then we could be measuring my velocity and acceleration in 3D space. So that would be many more parameters. So quite rapidly, we could start to describe me sitting here on my swivel chair, which has wheels, how I'm moving, how fast I'm accelerating, and so on. We could get very rapidly into 10, 12 dimensional parameter space that describes me. Now, the business of topology is to study, or one of the businesses of topology is to tell you the qualitative features of the parameter space of me and how fast I'm accelerating and so on, where I'm located. And there are many important features of that parameter space. The number one most important feature, I would say, is the dimension. And among the next most important things is this space orientable?
Mm-hmm.
And that really is a generalization of does it have a left, an outside or an inside? Does it have a front or a back? But it's kind of hard, and this frustrated me for a long time, to give a good definition of what orientable means. In all cases. So instead of that, let's think about well, what happens if I reverse the direction in which I am measuring one and only one of the parameters, leaving all the others the same? So if suddenly, instead of measuring the direction I was facing, measured as degrees from north, going in the clockwise direction, let's measure it as degrees from north going in the counterclockwise direction. Right? And this is an equivalent way of parameterizing the same space. All the numbers that described my situation would be the same, except for one of them that would have gone from a plus to a minus or a minus to a plus. That's all that would have happened. And that is definitely, whatever that is that should be an orientation reversing transformation of the parameter space. So it seems to me easier to describe what an orientation reversing transformation of an object is than actually to describe what it means to be orientable. Let me actually not really get into what orientability actually means too much further, except to say that one can give a definition of it. In some cases, you discover that you could say, for instance, do an orientation reversing symmetry of the space, or a swap of parameters, and then discover that you could smoothly deform that, say, back. There would be some way of smoothly deforming yourself back to the original parameter space, rather like the situation where you go around where you switch between front and back of the Mobius band. You could always get back to where you started by, say, rotating the Mobius band by a full turn. Anyway, this is orientability, and this is the esoteric thing about the Klein bottle that you asked about, and it's also the esoteric thing about the Mobius band, that they're non-orientable, and there are other spaces that are not orientable as well, of great importance. Now, the Klein bottle is it's a two-dimensional object, so it's a surface. So it's at the boundary of or it's certainly the sort of thing that we might expect to be able to visualize. But it can, because of its peculiar features, it cannot actually be properly constructed in 3D space. So we just know it exists as a formal space thing that maybe parameterizes some system, and it almost can be realized as a real geometric object in 3D, but not quite. The way you would construct a Klein bottle, if you had to make one purely abstractly, would be the following. You would take a ribbon, as before with the Klein bottle, with the Mobius band, but in this case, let's pretend the ribbon is not solely a ribbon and a flat ribbon, but let's roll the ribbon up to make a tube. So we have a tubular ribbon. So I do the same thing. I have some sort of pipe. And now I would like to glue the ends of the ribbon together. But if I just do that in the obvious, naive way, even if I impose some sort of twist, it won't matter, because what I will do is I will take a tubular pipe and I will attach the ends together, and I will make something like the inner tube of a bicycle or of a car. I'll make what we call a torus, or most people would know as a donut shape or a bagel shape, the surface of a donut or a bagel. But now bear with me, because this is going to sound absurd. what I can do is I can try to attach the ends of the tube to each other with an orientation reversing gluing procedure. So this would mean taking one of the ends, which I can view as a circle with, say, a clockwise direction chosen on it, and the other end, which I can view as a circle, again, well, with a preferred direction of travel on it clockwise, and I glue them together in such a way that as I'm doing it, I reverse the direction of orientation. Actually, sorry, I misspoke there. If I define a preferred direction of rotation on one end of the tube, I can carry that direction, remembering what the preferred way to go around the tube is. I can deform that all the way back along the tube, back to the other back end of the tube. So I can take my preferred direction from the front to the back, and I discover that I have this consistent direction of rotating around the tube at all points along the tube. And I bring the tube together, and I can glue the two ends together in such a way that they're consistently oriented. That's fine. That's how I get the donut. To get it so that they're not consistently oriented, I can't quite do it in physical space with an ordinary tube, because what I need to do is I need to glue one end of the tube to the other from the back, other than from the front. So what I do is I take the tube and I pass it in through itself, which you can't do with physical media, with actual physical pipes, and you glue the tube, one end of the tube to the other end from the back. And then, of course, that would give you some sort of singular join, and you smooth it out a bit, but we'll worry about that later. So the idea is a Klein bottle should be obtained by taking a tube and bending it around, passing it inside itself, and gluing the two ends that way. And this can almost be approximated in the real world. The only problem is the moment where you have to pass the tube through itself. And this is topology we're doing. We're not too worried about the qualitative properties, the quantitative properties of the object. So I can fatten the tube up to make it very wide at certain points and make it narrower at others. And this is how you get the familiar picture of the Klein bottle, which is let me try to describe it. This is not an easy thing to do in an audio format, but it's rather like it's a bulb-shaped vessel, and at the top of the bulb there's a stem that bends back, that goes up a bit and then bends down, passes through the bulb, and then opens up inside the bulb to meet the bottom of the bulb again, and wrap around like that. Now, if you don't know what it looks like, that explanation is certainly inadequate, and I encourage you to go look. Okay. Anyway, this is formally speaking, it's a surface. And what we've described here about making this Klein bottle, trying to make it in 3D space with this problem of passing the tube through itself, is what we're describing as what's called an immersion. So to simulate living on a Klein bottle, we can do that. Let's pretend we're ants or some other tiny bugs, and we live on the surface of this Klein bottle. And as we move around in physical space, most of the time we're just going to be there on the surface, and the thing is going to look like a surface to us. And there's one region or in space that's sort of problematic, which is where the bottle meets the surface, passes through itself. And here you have to, in order to simulate a Klein bottle properly, you have to follow the following rule. If you approach this point of intersection on one of the there's a tube intersecting a sheet. If you approach the point of intersection along the tube, you cannot jump from the tube to the sheet. And if you approach on the sheet, you cannot jump from the sheet to the tube. You have to continue through whichever one it was that you weren't on. And so remaining either on the stalk that's passing through the sheet, or remaining on the sheet that intersects this tube. So this is a textbook example of what's called an immersion. The Klein bottle, therefore, it's some sort of abstract surface. It can be realized if you just allowed yourself one extra dimension, of space. You can even sort of see how it would work. You just need to make it so that the tube doesn't actually meet the surface, even though it needs to, in 3D space, it needs to start on one side of the surface and pass through to the other side. That can't be done without introducing an intersection. In 4D space, you could use the fourth dimension to take a detour and avoid the self-intersection. So it's very nearly something that can be realized in 3D space, and it's not orientable. That's a Klein bottle.
Thank you. That's a really detailed explanation, and I really like how you connect one knowledge point to another, and I think it's really necessary in the explanation process. I was also wondering, who's your favorite mathematician?
Oh my goodness. Well, that's that is not a question I have a very good answer for. I will say that let's see, what do I think about this? There are many very famous mathematicians from history, and some of them have. I mean, all these people have many wonderful things. I am sure to recommend them. This has been mathematics is a very, very ancient enterprise. I suppose we don't really know how far back it goes, and we don't know the names of the many of the mathematicians of history, and I suppose prehistory. We do have the names, especially of the ancient Greek mathematicians, although they were by no means the only people to do mathematics 2,000, 3,000 years ago. And then in later days, mathematics is an international enterprise, certainly. And there's just so many mathematicians from all over the world. It has been in the recent past, even, I suppose, mathematics is still overly concentrated, and the present mathematics is overly concentrated in the rich Western world in a way that it shouldn't be, because one of the things I like about mathematics is, to an extent, it doesn't need any particular massive infrastructure. You can just do it. But what you do need is I think, is the support and encouragement of others. But my favorite mathematician. This is a difficult question.
How about give an example of a contemporary and an historical one?
Well, there's so much, because there's so much diversity and scope in the mathematical world. There's lots of different ways in which you might say such and such a mathematician was notable or praiseworthy. And then, of course, there are mathematicians who are personally, well, let's say that some of them left certain things to be desired. So even then, I think it's unfair to say, oh, such and such a mathematician is a favorite.
Right. How about one mathematician that you have been following or just been looking into his or her work recently?
I would say this. Mathematics is, when you do it properly, like I think everything, mathematics is difficult. Well, why do I say that? I say that because you start out by doing mathematics, and maybe you take classes, and people give you homework assignments and so on, and maybe you'll find those harder or easier, and there's certain variations in what you're given and so on, and you may prefer one thing over another. But once you start, or if you're so fortunate as to start doing mathematical research, then there's not really any reason not to do it to the maximum extent that you can, right? Yeah. And the mathematical world is enormous, and there are so many. I have this, you can't see it in the video, but I have this bookshelf, two of them in fact, and they're just completely full of mathematical books, all of which represent, I think, colossal amounts of labor.
Yeah.
And impressive, really dedicated work by very intelligent people working very hard on problems, and with the advantage of, but before them, I mean, this was what Isaac Newton said, that he had stood on the shoulders of giants, referring to the people who had come before. And if Newton believed that he had stood on the shoulders of giants, then we, I mean, I am no Isaac Newton, we should be extremely humble about the tremendous, the mountains of wonderful mathematics that have been produced for us to stand on and see a little bit further. And I say all this, but I would also say that one thing a trap you can fall into is to be intimidated by this. And perhaps you should be intimidated, because it is actually just such a colossal enterprise when so many very, very brainy people have come before us. But if you're intimidated, or if you are overly impressed by the work that has come before you, and then you think, oh my God, goodness, this stuff is so great, then you may lack the certain, let's see, how should I say it? You need a little bit, I think, of swagger, a little bit of, you need to overlook the fact that you are inheriting this tremendous wealth of stuff, and you need to take it a little bit for granted, and you need to just get on with the business of trying to prove something new. And then this is how the research works. So from this point of view, let me highlight a mathematician. I'm not going to say any mathematician is my favorite, and I don't particularly know this mathematician very well, but an experience that was very formative for me was when I was in graduate school one spring break. I think it was my second spring break. My advisor said to me, hey, why don't you go to this conference that they're having in Toronto? Now, I was coming from California, so going to Toronto in April was a little bit unpleasant, but the conference was quite good. Anyway, I was a grad student, and I took the red eye to save money. So I showed up sort of bleary-eyed, and I arrive in a room or in the Fields Institute at the University of Toronto, which is, it's this lavish building dedicated to holding math conferences and other events. I hope I'm not misrepresenting it. I think, yeah. Anyway, there are other notable mathematicians in this field. That I was just a starting out grad student. I was going to try to get a foothold in this field, do something of some value, and there were huge names there. Very, very famous people, tremendously intimidating presences, and I was feeling a little bit the worse for wear already, having been, having slept on the plane. And I got there, and there was a man walking around, let's say a middle-aged or slightly older gentleman, wearing, I'd only known him at his name from books that I'd read, Max Karoubi, a tremendously famous professor in K-theory, and walking around with a certain dignified air, and everybody knows him, and he's an expert in this field. He'd been publishing top-notch papers since the 1970s, and this is 30, 40 years later. And he, then there are other big names, and of course he's interacting with them and so on. And then he sees me and my colleague, who'd arrived with me, next to the Danish pastries, and I think we were even too nervous to take the coffee. And he said, "Hi, have a Danish." And the way he said it, he was so welcoming and so friendly, and he just talked to us. I don't think he said anything of any mathematical consequence at all. He wasn't really interested. He was just interested in who we were, and to welcome us into this event, and to make sure that we, at the very least, ate the pastries. Probably at this point we were hungry. So while I'm not going to say that Max Karoubi is my favorite mathematician, I don't think I met him at any event since then for whatever reason. I will say that this was a formative event for me, and I think a helpful one.
Sure.
And yeah, so I will say that there's a sort of a dichotomy here. Mathematics is this like tremendously impressive human enterprise of, I don't know how, I haven't even estimated how many mathematicians have ever lived, but incalculably many. And so many of them are tremendously able and have given us all this wonderful work, passed it down to us. But at the same time, you have to remember that many of these people are extremely friendly, and also just to get by in the business, you have to take your inheritance a little bit for granted and just say, okay, let's take all this as given, and let's see what we can do now.
Yeah.
And I suspect that this is not true only in mathematics, but most likely it's true in many fields of scientific research, for in particular, and probably elsewhere as well. I think mathematics maybe is I wonder if it could say it has a longer history than any of the others, perhaps, but I mean, this may not be especially consequential.
Yeah. I think math has the longest history, perhaps.
Yeah. But I also suspect that, yeah, if you're trying to do, well, maybe it does, maybe it doesn't. When we think about going all the way back to the very, very, very beginnings of what we know as mathematics, I think initially it may have been indistinguishable from physics and astronomy, for instance. But the point stands that in many fields of human endeavor, we have a colossal inheritance, and we should. It's a hard thing to do. We should be both respectful of that and reverential towards it, but not to the point where we don't just say, well, okay, what can we do now?
Yeah.
I think that's the important thing.
Yeah, and lastly, I wanted just to ask, a lot of my listeners, they're also really into novels and classics. So what is your favorite classic right now? Even though it's not really related to math, but is there a favorite classic in your English studies?
All right. Okay. Do I have a favorite classic? Well, let me say that a book that I've read several times. I haven't read too many books more than once lately, but one that I have read several times, and I think I always get something from is the novel Catch-22.
Oh,
I haven't read that for several years. Maybe I'll read it again and think, oh my goodness, what is this? What is this nonsense? But I really doubt that. I think this is a wonderful work, extremely funny, and well, I suppose that there are. I mean, it's a serious novel with a serious anti-war message, set in the Second World War, but about perhaps other wars. But I think what it has is, on top of its seriousness, is it has a certain lightness of approach, and it highlights the absurdity of our situation. And I think this is something that's also valuable to me. That in spite of all the seriousness of everything, what we do, our lives, and so on, they all have a slightly absurd quality to them, and it's good to remember that, so that in times of either great triumph or great difficulty, you remember that well, the whole thing is a little bit ridiculous, and perhaps this will make you may not get too carried away by your triumphs, and maybe not too overwhelmed by your difficulties.
Yeah, that's a really profound statement to make at last. Yeah, you seem to be a very humble mathematician, and I noticed that a lot of mathematicians are really humble. I mean, some of them are really egotistical, but yeah, you're
Well,
humble.
yeah, I think that I think, well, let's see. I've been on a journey, um, uh, as I suppose, and I continue to be on a journey. Uh, I think we maybe start out thinking, well, you learn something new, and you're like, my man, this mathematics, this is difficult. It's you have to sit down and think and so on, and then maybe this certainly happened to me in high school. I thought, no, you know what? I got to the point where I could do everything that they were asking of me, and I thought, gosh, mathematics is not hard. It's easy. You can just do what they tell you to do. You just follow the rules, and you do the algorithm, carry out the procedures, and then you get to the right answer, and that's no problem. Math is easy. And and then I went to college, and math was uh, easy for a while because that's what they were asking me to do. But it turns out that in the end, as I said, um, if you are going to do research in some field, whatever it is, uh, then it turns out you were right all along. Math is hard. Everything is hard if you're doing research in it, because it's not hard, there's no point. You should always be doing it to the maximum of your ability, which means a considerable amount of anguish. And I think this is true for many mathematicians. So the typical process is there's some problem that I have that I would like to solve that seems just completely impossible. And maybe through talking to other people or good fortune or thinking very hard about it for a while, maybe it becomes easier. I can solve some special cases. And maybe if you're really fortunate, everything clicks into place and you can solve the original problem that you wanted to solve. And then having done that, in the research story, I mean, there's the problem of having to write down what you did and explain it to others and so on, but let's put that to one side. In the research story, once you have solved that problem, you are no longer thinking about that problem. So once you know the answer, you've moved on, and now you're thinking about a new thing to which you don't know the answer. So that is intrinsically humbling.
Yes.
Because at no point in my research career do I understand what I'm doing. Always lost.
Yeah.
And as soon as I cease being lost, I find some new way to get lost. It's a constant stream of just finding math hard.
Yeah.
And I think we were just correct all along.
Yeah.
Math is fundamentally difficult because once you've understood it, you move on.
Yes. So are you in constant happiness, or you're tired of being dragged along?
Well, to tell you the truth, I wish I was being I think like many of my colleagues, I wish I had more time to dedicate to research and had well, it's hard to say. Let's say this: my job seems to be 50% research, 50% teaching, and 50% other stuff, which gives you some idea. There just isn't enough time to do all the things. So I am not. I don't think I will ever become tired of doing mathematical research, and I just wish I had more time to do it in. I also don't think I will ever become tired of teaching.
Yeah, it seems like you're a really
joy.
good teacher, and your lectures must be really funny as well, so people pay attention. Thank you.